Hello friends, welcome back. In this part of the series of the lecture entitled Engineering Disordered Fibrous Materials via Theory of Fiber to Fiber Contacts, we are specifically going to talk about how to calculate the number of fiber to fiber contacts in anisotropic fibrous materials. So, in this regard we need to first look at the orientation of the fiber in a three-dimensional spherical coordinate system. Here we have considered half of the sphere due to its symmetry. So, if you see, there is a fiber which is shown here with a pink line which is making an angle theta with the z axis. We call this angle as out of plane orientation angle, and the projection of this fiber on the xy plane is phi, which is shown here, and this fiber covers a defined space dA, which is calculated by means of this portion which is r d theta and r sin theta d phi. So, if you take the product of r d theta and r sin theta d phi, we can actually calculate the area occupied by this fiber which is occupying a space dA on this sphere. So, why we are interested in this particular region? Because you will see here that if the radius is unity, then this element dA has the area sin theta d theta d phi. Okay. But this is the case where the fiber orientation is random in nature. That means, the fibers are distributed uniformly within the structure, okay. But this may not be the case every time. So, if you look at the right hand side figure, then you will see there is a term omega theta phi, which actually represents the probability density function of finding a fiber with an orientation angle theta and phi. Here theta again is a polar angle or out of plane orientation angle, and phi is the in plane orientation angle. So, in this case, if you see here, omega theta phi sin theta actually represents the proportion of fibers or the relative frequency of fibers covering the whole sphere. That means, or omega theta phi is the probability density function which represents how many fibers are covering a defined region. In this case, it is dA. Okay. So, if you multiply omega theta phi with sin theta d phi, you will be able to calculate the relative frequency of fibers. So, let us try to calculate the three-dimensional fiber orientation distribution function. Suppose the probability of finding the orientation of a fiber infinite small range of angles theta and theta plus d theta and phi plus d phi be omega theta phi sin theta d phi. So, this is the relative frequency of a particular fiber having orientation angles theta and phi. So, as we know, there is a particular property of relative frequency that if you sum all the relative frequencies, then it will be unity. So, if you take the integral of omega theta phi sin theta d phi, then it will be unity. So, this is the most important normalization condition that needs to be followed in every fibrous material. So, let us see how we can make use of this orientation distribution in the next few slides. Let us say there are two fibers A and B, fiber A with an out of plane orientation angle theta and phi is the in plane orientation angle, and then there is another fiber B which is having an out of plane orientation angle theta dash and in plane orientation angle as phi dash, and the angle between the axes of these two fibers is chi, which is shown here. So, when these two fibers come in contact with each other, then apparently they will form a parallelepiped around their periphery, as you can see. This parallelepiped has a thickness 2d and the fiber length segment L, which is involved in forming this parallelepiped. So, using the spherical coordinate system, the vector A, in this case is the fiber A, would have the orientation theta and phi. Accordingly, using the basic principle of stereology, we can calculate the projection on the x axis as sin theta cos phi, on the y axis would be sin theta sin phi, and on the z axis it would be cos theta. Similarly, for fiber B, the vector coordinates would be sin theta dash cos phi dash, sin theta dash sin phi dash, and cos theta dash. So, if we are supposed to calculate the angle between the axes of these two fibers, then we need to make use of simple vector analysis, and that is the direction of cosines. So, the direction of cosines cos chi is defined in terms of the product of these two vectors A dot B and divided by the magnitudes of these two vectors, which are denoted by double mod. So, A dot B is equal to sin theta into sin theta dash cos phi dash plus sin theta dash sin phi dash plus cos theta dash. The magnitude of this vector A would be unity, as is very simple to calculate. Similarly, for B it will be again unity. So, if you try to calculate the angle between the axes of these two fibers, it will be cos of chi is equal to cos of theta, which is theta is the out of plane orientation angle of fiber A, cos of theta dash, which is the out of plane orientation angle of fiber B, plus sin of theta into sin theta dash cos of phi minus phi dash. So, phi is the in plane orientation angle or azimuthal orientation of the fiber A, and phi dash is the in plane orientation angle of fiber B. So, we will be making use of this formula later on when we are going to calculate the number of fiber to fiber contacts in anisotropic fibrous materials. The fiber to fiber contacts in anisotropic material would be formed by means of a parallelepiped. So, if we know the volume of the parallelepiped, so in this case this 2d is the thickness of the parallelepiped or the height of the parallelepiped, and L is the fiber length segment which is involved in forming the parallelepiped, and chi is the angle between the axes of these two fibers. So, volume of the parallelepiped formed around the fiber segments would be equal to 2d into L square sine of chi, where we know that chi is a function of theta, theta dash, phi and phi dash. Now, if we are supposed to calculate the probability of formation of a contact between the fibers A and B, then it would be the volume of this parallelepiped, as you can see here, to the total volume of the fabric. So, volume of the parallelepiped we already know, we have already calculated 2d L square sin chi, and let us say capital V is the volume of the whole fabric. So, now we know what is the probability of a formation of contact between the two fibers, but as we know there are n number of fibers making n minus 1 contacts. So, we need to calculate the average number of fiber to fiber contacts on a particular fiber. So, let us say the fiber A makes a contacts with well defined number of fiber B. So, in this case n theta phi, which is shown here, denotes the average number of fibers that come in contact with the fiber A. Obviously, n fiber makes n minus 1 contacts. So, this is the reason you have n minus 1, and then we simply take the orientation averaging approach. So, previously we have calculated the probability of the formation of a single contact, which is denoted by P here, and we multiply it with the relative frequencies of the type of fiber B which are present in the system. So, if we multiply with the relative frequencies of fiber B which are present in the system and probability of the formation of a single contact which is shown here with P, then we can calculate the average number of fibers that contact fiber A. So, putting the value of P which we have calculated earlier, then n theta phi will be equal to 2d n minus 1 L square by V, and then we integrate this equation in terms of omega theta dash phi dash sin chi sin theta dash d theta dash and d phi dash, and we can define this integral in terms of j theta phi. So, where j theta phi is this integral. So, we can simply write this formula assuming that n is very large. So, as you can see here, n is much larger than 1. So, n theta phi is equal to 2d n L square divided by V into j theta phi. We can calculate the average number of fibers that come in contact with fiber A, but since we know that there are different types of fibers in the system, then we would like to know how many average number of fiber to fiber contacts in an anisotropic fibrous material can take place. So, in this scenario again we make use of orientation averaging approach, which is, for this we calculate the average number of fiber to fiber contacts on an arbitrary fiber which is given by n theta phi, which we have calculated earlier. That was just for fiber A. So, fiber A was coming in contact with defined number of fibers and the relative frequency of the fiber A itself. So, which will give us the average number of fiber to fiber contacts on an arbitrary fiber. So, this will be equal to 2d n L square divided by V into I. So, I is a kind of global orientation parameter which can be defined in terms of double integrals j theta phi omega theta phi sin theta d theta d phi. So, we can also calculate the number of fiber to fiber contacts per unit length of fiber, that is we denote it by means of NL bar, as you can see here, which is equal to n bar divided by L. We already know the expression of n bar. So, we can simply put that expression here and we can calculate in terms of the total length of the fibers in volume V and in terms of fiber diameter d and the global orientation parameter I. So, we can convert this expression of NL bar in terms of fiber volume fraction like we have done it earlier in random fibrous materials. For example, Vf in this case would be the fiber volume fraction, which is the volume of the fiber divided by the total volume of the fabric. So, volume of the fiber would be, considering the fiber to be cylindrical, then it will be pi d square by 4, which is the cross sectional area of the fiber, into the length of the fiber. So, dividing pi d square by 4 L by V would give us the fiber volume fraction. Inserting L by V would give us the expression of NL bar in terms of the fiber volume fraction, fiber diameter and global orientation parameter. So, NL bar is equal to 8 Vf by pi d I. So, these are all measurable quantities. We know the fiber volume fraction, we know the fiber diameter, we can measure the fiber orientation distributions of a particular fibrous material, then we can calculate how many number of fiber to fiber contacts per unit length of the fiber. Now, the next step would be to calculate the mean distance between the fiber to fiber contacts. As we have done it earlier in case of Van Wyck's model, we took the reciprocal of NL bar, which is the inverse of average number of fiber to fiber contacts per unit length. Then if we inverse this parameter, then we will be able to calculate mean distance between the fiber to fiber contacts expressed as B bar, which is again can be expressed either in terms of capital V and capital L, which is the volume of the fabric and the length of the fibers in this volume, or we can also express it in terms of fiber volume fractions. So, which will be equal to pi d by 8 VFI. So, this is an important expression because we are able to calculate the mean distance between the fiber to fiber contacts in an anisotropic assembly on the basis of fiber diameter, fiber volume fraction and the global orientation parameter, which denotes the alignment of fibers in the system. We can also calculate the total number of fiber to fiber contacts in fibrous assembly of volume V containing n fibers. So, if you denote NV as total number of fiber to fiber contacts in defined volume V, then it will be simply expressed in terms of average number of fiber to fiber contacts in the system with the total number of fibers present in the system. So, why we have divided n by 2? Because 2 fibers actually make 1 contact. So, in order to avoid the double counting, we divided by 2. So, NV can be expressed in terms of D L square by V into I. So, this is a simple formula to calculate the total number of fiber to fiber contacts in a fibrous assembly of volume V containing n fibers. So, let us see how our model can be useful for calculating the number of fiber to fiber contacts or the mean distance between the fiber to fiber contacts in case of 2-dimensional random fibrous materials. For 2-dimensional random fibrous materials, all the fibers should lie in a plane parallel to the xy plane. Therefore, theta will be equal to pi by 2, because theta is the polar angle or the out of plane orientation angle. In this case, theta will collapse and phi is randomly distributed and the density function should be calculated by means of Dirac's delta function. Why Dirac's delta function? Because Dirac's delta function allows us the collapsing of theta, which is the out of plane orientation angle, in a mathematical manner. So, if you see, let us say omega theta phi, which is the density function, which is equal to the omega naught 2d. Now, this is the new orientation density function for a 2-dimensional random fibrous material, that we multiplied with the Dirac's delta function, which is delta theta minus pi by 2, and we make use of the property of Dirac's delta function, which is expressed here. If you have an integral lying between minus infinity to infinity, and if you have a function f t, if you multiply with delta t minus t, which is the Dirac's delta function, into dt, that will lead to a well defined value of a function at a particular time period, in this case which is t. Otherwise, in our case it will be pi by 2. So, it will be f of theta or f of pi by 2 in this case. So, as we already know the normalization condition that we earlier calculated, our orientation density function should satisfy this normalization condition. So, if you insert the expression of omega theta phi from here and insert in this equation of normalization, you will be able to calculate a constant value of orientation density function to be 1 by pi. So, once you calculate this value of omega, then we can again go back, we can express omega theta phi in terms of 1 by pi, which we have just inserted 1 by pi here in place of omega naught 2d. So, new omega theta phi will be equal to 1 by pi delta theta minus pi by 2. So, if we start calculating the expression of I and j or the values of I and j, we have to simply replace omega theta phi, which is expressed here as you can see, and it should be replacing in the original equation, and this will be the new orientation density function for us. So, if you see the theta will collapse, that means f of pi by 2 which is the function is sine of theta. So, f of pi by 2 will be sine of pi by 2, which is unity, that will simply lead us to the expression of 1 by pi multiplied by the integral 0 to pi j pi by 2 phi into d phi. So, in this way we can also calculate j pi by 2 phi. We simply make use of Dirac's delta function here again, and you will see that the value of j for a 2 dimensional random fibrous material would be 2 by pi. You can also see that sin chi can be expressed in terms of sin phi minus phi dash. Then you can again integrate this equation to calculate the value of I, which is again 2 by pi. So, for a 2 dimensional random fibrous material, the value of I and j would be same, which is 2 by pi. You can also calculate the total number of fiber to fiber contacts in a 2 dimensional random fibrous assembly of volume V containing n fibers, or we simply put the value of I and we can get the NV in terms of 2d L square by pi V. So, in this way we are able to calculate the values of I and j, and accordingly we can calculate the mean distance between the contacts and number of fiber to fiber contacts. So, let us now consider a case of 3 dimensional random fibrous material. In this case the orientation density function is independent of theta and phi. Again we have to revisit our normalization condition. Now, our new orientation density function omega naught 3d would be simply the inverse of the integral between 0 to pi and 0 to pi again sin theta d phi, which will be 1 by 2 pi. So, we can recalculate the values of average number of fiber to fiber contacts, since we know the values of j, because that will be simply equal to pi by 4, the way we have calculated for 2 dimensional random fibrous assembly, and the value of I would be also pi by 4. So, once we calculate the values of j and I, then we can reinsert the value here for in the expression of mean distance between the fiber to fiber contacts, which we have formed earlier. So, it is pi d by 8 VFI. So, if you insert the value of I as pi by 4, then you will see B bar is equal to d by 2 Vf. If you remember, this expression was also formulated earlier by Van Wyck, and we can also calculate the total number of fiber to fiber contacts in 3 dimensional random fibrous assembly of volume V containing n fibers, that is expressed in terms of pi by 4 d L square by 4 V. So, you can see that the anisotropic model is a generalized model, and we can calculate the values of I and j and other orientation parameters for a 3 dimensional random fibrous material, and we can get the same mean distance between the fiber to fiber contacts as we got it earlier using Van Wyck's model. But the question is, how should we make use of these models, or how should we make use of the calculation of number of fiber to fiber contacts in fibrous material? In this case we have to make use of a certain volume, because volume is difficult to measure specifically for a fibrous material. So, we have to consider a mesodomain. What is a mesodomain? A mesodomain is just like a unit cell which has a certain thickness. So, it is a repeating unit within the fibrous material. So, we basically make use of continuum approach, where we know if you have a smaller volume, then you have less number of contacts. If you have a bigger volume, you have more number of contacts. So, this mesodomain has a unit cross sectional area, as you can see, and it has a thickness Bj bar, which is the mean distance between the 2 successive contacts projected on a z axis or on the thickness direction in this case. If we are supposed to calculate the number of fiber to fiber contacts in this mesodomain volume dV, then we have to make use of continuum approach. So, in this case number of fiber to fiber contacts is proportional to the volume of the system. So, NdV is equal to Nv into Bj bar Ac by V. So, V is the total volume of the fabric, Nv is the total number of fiber to fiber contacts in the volume V, Bj bar is the mean distance between the fiber to fiber contacts projected on the J direction or Z direction or in the thickness direction, and AC is the unit cross sectional area. So, since we know AC is unity, then we also know that Nv is equal to dl square by Vi, we have calculated earlier. We also know that Bj bar is equal to B bar Kj. So, B bar we have actually calculated, expressed in terms of V by 2 dLi into Kj. Kj is the directional parameter which represents the projection of the fiber element between the two contacts on a defined plane or on a defined direction. So, using the basic principles of stereology, we can calculate the NdV by making use of the expression of fiber volume fraction, which is pi d square by 4 VL, and one can calculate the total number of fiber to fiber contacts in a meso domain, which is a function of fiber volume fraction, fiber diameter, and Kj is the directional parameter. So, if you remember, omega theta phi sin theta d theta d phi is the element or is the relative frequency of particular fiber which is projected on a particular direction, which is cos theta. So, if you take the projection of this fiber element on this direction, it would be cos of theta. So, the proportion of fibers which are present or which are aligned in this particular orientation angle, it will be omega theta phi sin theta d phi. If you multiply with cos of theta, it will give us the directional parameter Kj expressed in this form of integral. So, we already know the density function in case of 3-dimensional random fibrous assembly, which is 1 by 2 pi, and we can calculate the value of Kj, which comes out to be half for a 3-dimensional random fibrous assembly. So, you can insert this value of half and you can put it back here, and you will get the expression of NdV as Vf by pi d square for a 3-dimensional random fibrous assembly. So, in the next series of lectures you will see that we will be making use of NdV, because it is a useful approach for calculating the number of fiber to fiber contacts in a meso domain, because this meso domain would experience the same level of strain, for example, in tensile loading or in compression loading, and it would reflect the strain experienced by the fibrous assembly or fibrous material. So, let us take an example for calculating the number of fiber to fiber contacts in a meso domain. So, let us assume an air laid non-woven of mass per unit area of 250 gram per meter square and the thickness of 5 millimeter, that can be modeled as a 3-dimensional random structure. So, if we are supposed to calculate the number of fiber to fiber contacts in this meso domain, then we can consider the value of Kj to be half. So, this non-woven is made up of polypropylene fibers which have diameter of 30 micron. Now, considering a meso domain in this non-woven, calculate the number of fiber to fiber contacts per millimeter square. We also know the polypropylene fiber density to be 0.91 gram per centimeter cube. So, the given parameters in this problem obviously are that is a 3-dimensional random fibrous material. So, obviously in this case the Kj would be half, as we discussed earlier. The diameter of the fiber would be 30 microns. So, we convert all the units into SI units. So, 30 microns will be 30 into 10 raised to minus 6 meters. The density of polypropylene fibers would be 910 kg per meter cube. Similarly, the mass per unit area of the fibrous assembly is given as 250 gram per meter square, that can be easily converted into kg per meter square, and the thickness of the fibrous assembly is also given to us, which is 5 millimeter, which is 5 into 10 raised to power minus 3 meters. So, we are supposed to calculate the number of fiber to fiber contacts taking place in this mesodomain. So, the solution is, first we are supposed to calculate the fiber volume fraction. We know the basic formula of fiber volume fraction, which is defined as fiber volume to the fabric volume, and the fiber volume is mass upon density and the fabric volume is area into thickness. So, we can simply convert into mass per unit area as W, which is the GSM of the fabric. We also know the thickness of the fibrous material and rho f, which is the fiber density. So, putting all the values which were given to us, we can calculate the fiber volume fraction as, in this case would be 0.055 or 5.5% is the fiber volume fraction. So, the number of fiber to fiber contacts in a mesodomain, we know it is NdV is equal to 2 Vf by pi d square into Kj. As we have already calculated the value of Kj for a 3-dimensional random fibrous assembly, which is half. So, you can put all the values of other given parameters. In this case, fiber volume fraction is 0.055, fiber diameter as 30 microns, Kj is half. So, we can calculate the number of fiber to fiber contacts per meter square or in a mesodomain. So, which comes out to be nearly 19 contacts per millimeter square. So, in this case, we were able to calculate the number of fiber to fiber contacts in the mesodomain, and in the next series of lecture we would be looking at the applications of this mesodomain, how we can make use of the number of fiber to fiber contacts in a given mesodomain for predicting, let us say, the compression properties, tensile properties or even the shear properties. Thank you very much.